Physics guys, here we go. I've got a bunch of pictures up here, and I want to go through all of this because this is what we've explained in terms of force and friction. This is that same block on an inclined plane where I pulled this triangle out so you can see where all this stuff comes from and how to find it. I've done all the calculations for you so I can just tell you what they are. And last but not least, this is equilibrium, and that'll be a little bit more to explain. Now, first thing, force. Well, we need to know about this block's weight. And like I said, weight is not the mass. So when I say, hey, what's the weight of this block? It's not 20 kilograms. It's 20 kilograms times the acceleration due to gravity. Now, the positives and negatives are very important in certain aspects because we need to know that friction goes against some force being applied. But for this particular problem, I don't even need to know. What I'm going to find out is how much force do I need to apply to overcome the friction on this box. So I have a whole bunch of formulas up here. The weight of the object is its mass times the acceleration due to gravity. The normal force is that perpendicular contact force that keeps this object from sinking through the floor or accelerating upward, right? So it's going to be the same magnitude, but in the opposite direction of its weight, or the force of gravity. Now, this frictional force is what's going to pull it back. If I wanted to push this block this way, this frictional force is going to hold me back. Okay, and that's just this mu. You know, the coefficient of friction. This one's pretty sticky. I made it a half instead of something smaller like I've used in class. Right. So we take this object and we find out what its weight is. Well, its weight is negative 196 newtons, because that's negative, we'll call it down negative for now, negative 196 newtons pulling downward. The normal force is the opposite, same magnitude, 196, but it's pushing upward, right? And why do I need that normal force? Because to find friction, the force of friction, the amount of pullback, it's that mu, that coefficient of friction, times the normal force. So I have my normal force, I have my coefficient of friction, I multiply those two things, and half of 196 is actually 98. I don't know why I wrote 96. Let me grab my marker and fix it. Sorry, I'm off camera. There we go. 98, silly. There we go, I found my first mistake. Whee! The other ones I used a calculator, so I know I didn't make a mistake. So it was in the correct mode. So there's friction. So how much force do I need to apply? I need to apply at least 98 newtons of force to make this block start to go. Sound good? Great. Now let's move on to the inclined plane. Now I've taken this and now I'm lifting it up and I've got it up at a 35-degree angle. So my X component, my component parallel with the ramp itself or the inclined plane itself is how much pull is there down this ramp. You stand on a hill, how much pull do you feel parallel to that hill? Because you don't really feel the pull into the hill, you feel it pulling you down the hill. How much is the normal force? You know, you're pushing into the hill, but the hill is pushing back at you, and you're not sinking into the hill, and you're not accelerating up off the ground. No, you're just sticking to the hill. So that's the normal force. And there are equations that go with it. And of course, they're all components of the actual weight of the box. Now, I've taken that weight, or the force of gravity on that box, and I've taken all of these components, and I've put them up here, and I've stuck it right here, and I've created this right triangle. where this is the parallel force down the hill. And it's the side that's opposite that 35-degree angle. And this component here, the normal force, is the side that's adjacent to the angle, right? It's right next to that angle, so it's adjacent. So I'm going to use my trigonometric functions and find out what these components are. And you know what I didn't do, and I apologize, I'll write it out now, because I did write it out down here, but I didn't write it out over here. So I'm going to write out the big equation first, instead of just the formula. If I'm looking, oh, that's why I did it, because I already knew this. If I'm looking for this side, right, I'm looking for Fn, right? And so the cosine of 35 degrees is equal to that Fn, and that Fn is over Fg, which is, we already know, 196 newtons. Okay? Now, how do I solve for Fn? I just multiply both sides by 196. So, multiply both sides by 196. That goes away, 196. All right, and so 96 newtons times the cosine of 35 is going to give me the magnitude of that normal force. And what I came up with is just about 161 newtons. The same thing holds true here. It would be the sine of 35 is force parallel over 196. We multiply both sides by 196. So it is the same thing. 196 newtons times the sine of 35 degrees gives me my force parallel. And it's just about 112 newtons. And that seems reasonable, right? This is much closer to that 196 than this 112, right? So there's a pull down the hill of 112 newtons, just about almost half of what that force of gravity is. And then there's, closer to root 3 over 2, or that's cosine of 30. 161, that's great. All right, got it all done, except for this last thing. The last thing that we're going to talk about in terms of force is keeping an object that's hanging, a sign per se, at equilibrium. So I made this a 200 kilogram sign with 2 cables holding it. And because this triangle is so small, I rewrote it over here so I could do all the math. This is 200 kilograms. The weight of the object is 200 kilograms times 9.8 meters a second squared. So the weight is 1,960 newtons. Well, how many cables are holding it? 2. So 2 cables are sharing that vertical weight. So we need to know how much vertical force each of these guys is carrying, and they would split it. If they didn't split that weight, this sign would shift over or shift over. If one of those cables was pulling harder, then there would be more upward force on this side and it would start to shift this way. If this guy was pulling with more force, the whole thing would shift over this way. So they're both sharing that 1,960 newtons. Therefore, each is holding half, right? So each is holding 980 newtons. of that weight. Great. Now I know what this vertical side is for each of these triangles. Well, if I know that vertical side, and that's the side that's opposite the angle that I've been given, I can use the sine function. So I'm going to write it all out, and then I'm going to solve. The sine of 50 degrees is equal to the opposite side over the hypotenuse. And that's what I'm looking for. I'll call it T1, because that's what I call it on the triangle above. And I'll fix it here. T1, T1. Now, in math, I can go through the whole thing. It takes 2 extra steps, and it takes a bit longer. Just know that these 2 things, you can swap them. Through algebra, you can swap them. So T1 is equal to 980 divided by the sine of 50. If you put that into your calculator, you get about 1,275 newtons. Conversely, let's look for T2. T2 and T2. Same idea. The sine of 70 is 980 newtons over T2. Switch my sine 70 and T2. T2 is 980 newtons divided by the sine of 70. T2 is 1,043 newtons. As this gets closer and closer and closer and closer, this value should get closer to 980. So this should be a bigger magnitude. It is. All right, so we've checked our work. It seems reasonable. We have a lot more force on this thing that's at a shallower angle. It's farther out. It's got to pull harder to get more upward force or get that same amount of upward force. Makes perfect sense. That's our logic. And that's how we find equilibrium with something hanging on cables. That's what we've done for the past couple days. This is just a reminder. And hey, now that we're caught up, let's do some work. Let's take a quiz. Thanks for your time, guys.